This is the first seminar of our COINFLIPS project seminar series. COINFLIPS, for many of you are aware, it's a DOE microelectronics project focused on probabilistic neuromorphic computing. And kind of in that spirit, I don't think we could start off with a better speaker to kick off our seminar series than Dr. Supriyo Datta from Purdue, who is going to introduce us to the concepts of p-bits. Dr. Datta has kind of been one of the leaders in probabilistic computing field for a while, and he's done exceptional work over many years in nanotechnology and nanoelectronic devices. And he is a member of the National Academy of Engineering, fellow of the American Physical Society, IEEE. So I think we're very honored. I'm very honored to have him kind of kick us off and introduce this area of probabilistic computing. And so in that sense, I'll go ahead and turn it over to Dr. Datta. Thank you.
Thank you very much. Thank you all for coming, and thanks for the kind introduction. Can you hear me clearly?
Yeah, we can hear you pretty well.
Perfect. Okay. As mentioned, we've been working in this area for a few years now, and what I'll be talking about today, there's a number of people who have contributed over the years. Some have graduated and moved on, and some are still working in our group. And yeah, just before I start, I wanted to acknowledge all the people who have contributed to different aspects of what I'll be talking about. Now, this idea of this p-bit as something between a bit and a qubit. So bit, as we all know in digital computing, that's the unit of information, right? It's either 0 or 1. On the other hand, these days we hear a lot about qubits, which is the superposition of 0 and 1. And what we have introduced is this concept of a p-bit, which kind of bridges between a bit and a qubit. In the sense it's classical, just like a bit, but then, as I'll try to explain, it does have many of the features of a qubit. Not all, but many. Now, as you know, bits can be represented in many ways, and one way to represent it is in terms of the two states of a magnet, the two stable states of a magnet. On the other hand, for qubits, of course, the usual representation is single spin. That's the best physical representation for what you'd call a qubit. Now, as you know, magnets are like a collection of strongly interacting spins, which because of their internal interactions have these two stable states. Now, one of the well-known problems of magnets is that when you make them small, nanomagnets, they tend to become unstable. And of course, in the context of standard memory and logic, that's a disadvantage. And so people try to design magnets so that they will be stable. And what we have been arguing is that an unstable magnet would be a very good physical representation for a p-bit. But of course, just as with bits and qubits, there are many possible representations. This is just one of them. But it kind of helps to illustrate how this concept is between a bit and a qubit. And as I say, what I'll try to convey is that it does incorporate many interesting features of qubits and thereby provides a nice conceptual bridge from our familiar world of digital bits to this new world of qubits. Now, to understand this relationship, let me just quickly explain one interesting difference between bits and p bits and q bits. And that is, when you use bits, they are in a state of zeros or ones. And so you have a state, say 1 0 0 1, and then you use a gate to transform it into something else, and so on. And that's how you process information. You go from one definite state to another. Whereas when you have a probabilistic circuit, then from 1, you don't go to a 1 or a 0, but you go to 1 with some probability and 0 with some probability. And so when you want to describe the state of this probabilistic circuit, you need this probability distribution function. You have to you have to state the probability of all the different possible configurations. So if you have this small n number of bits, then the number of possible configurations is 2 to the power n. And so we need this probability density function, which has 2 to the power n components. Okay? And if you want to describe how the system evolves with time, then you say, okay, here's the probability distribution function at time t, and this is what it is at the next instant in time. And you have a matrix, 2 to the power n by 2 to the power n matrix that's connects them. Now, viewed this way, you can kind of see why a very important point, and that is that as n increases, this 2 to the power n increases very fast. So with n equals 10, 2 to the power n is about 1,000. But with n equals 40, it's like 1 trillion. And I'd say a lot of the power of either probabilistic or quantum computing essentially comes from this difference of being able to operate in this 2 to the power n space. And that is the point I want to stress, that people often cite all different examples. But the first question I often ask is, yes, but is it working in this 2 to the n space or in the n space? Right? Because a lot of the power of what we'll be talking about comes from this 2 to the n. And here you can see also the relationship to the quantum, the qubits, because there, I guess, with p bits, you have this probability function, which is all positive. Whereas with qubits, you have this wave function, which is complex, and it's connected by a unitary matrix U. So mathematically, they look very similar. But of course, the all-important difference is that with p bits, you're dealing with positive matrices, positive quantities. Here, it's complex. Okay. Now, so what I'd like to go through, because this is roughly an outline of what I want to talk about. And the first couple of points, these are, some of you may be very familiar with it. Please bear with me. But I wanted to stress this importance of this 2 to the n space. So let me go through that. Now, one way to think about a p-bit could be, many of you are probably from a solid state or semiconductor background. And you know that we generally think in terms of these 1 electron levels, which are occupied or unoccupied. And you could think of each one as kind of a p-bit, really, because if it's occupied, it's 1, unoccupied, 0. So you have this Fermi function, which tells you whether a particular level is occupied or not. And F1 is the occupation, 1 minus F1 is the probability it's not occupied. And if you had 2 energy levels, that's like 2 p-bits, but then there would be, in this configuration space, you'd have 4 components. Now, so usually we think in terms of the 1 electron space, but you could write down the probabilities in the 2 electron space, that what's the probability both are unoccupied, or one is occupied, or both are occupied, etc. Now, of course, usually we'd say, oh, if you want to know the probability of 0, 1, that the first one is empty and the second one is full, it's just 1 minus F1 times F2. But this factorization only holds for non-interacting electrons. See, and this is the thing that we have got used to because, using mean field theory, etc., we always tend to think in terms of these non-interacting electrons. And so we always work with these one electron occupation functions. But in the 2 to the power n space, this factorization only holds for non-interacting electrons. And what that means is, if your energy function can be written as just in terms of linear terms, where this S is a variable which is 0 or 1, which tells you whether the ith state is occupied or not. But if you have interactions, and you could have 2-body interactions, 3-body interactions, and more. If you have interactions, then this factorization doesn't work at all. Now, when there are interacting systems, then of course the general law is this Boltzmann law, which tells you that if you have to think in terms of these 2 to the power n states, and the probability of any of these states is related to the energy of that configuration. And this is the configuration, energy is in this 2 to the power n space. And so, for example, if you had 2 levels that were very close to the chemical potential, then they would both have half a probability of half a chance of being occupied. And so if there was no interactions, all 4 possibilities would be equally likely. But if you have interactions, then you could have a situation where if 0, 1 and 1, 0 are highly occupied, or 0, 0 and 1, 1 are highly occupied, depending on whether the interaction is attractive or repulsive. And this kind of a distribution is not factorizable at all. Okay? Now, and this is a point I want to stress because when I've often run into people who are familiar with who work with semiconductor physics and who are familiar with the Boltzmann approximation to the Fermi function. And I had questions like, well, why, when you talk about Boltzmann machines, why don't you talk instead about a Fermi-Dirac machine? That would be more general. And the point I make is, no. I mean, what we are talking about is the Boltzmann law, which is in this 2 to the power n space, and which is actually a very general law. It is the central principle of equilibrium statistical mechanics, see? And that is very different from this non-degenerate approximation that you use in the one particle space. It's got nothing to do with that. This Boltzmann law is very general. It describes this. And Fermi-Dirac, Bose-Einstein, everything can be deduced from the Boltzmann law. So that's the most general version. And this is this central principle. And why don't we use it more routinely? Well, because it is inconvenient to use because of this 2 to the power n space. Because as I mentioned before, as soon as you have 40 levels, you got 1 trillion configurations to deal with. Now, so one of the things people do then in terms of dealing with this 2 to the power n space is sampling. And there are different methods that have been developed, and there are different approaches, and they're related. And one of the common ones is this Metropolis Hastings, which again, many of you are probably familiar with. And this idea is that, and the challenge is, what you want to do is, of course, you cannot really calculate the entire probability distribution, but you want to generate samples which obey the correct probability distribution. And this algorithm lets you do that. So what you could do, so the way this works is you propose a configuration, then look at how much the energy changes with respect to the last one. That's the delta E. And based on that, you either accept or reject the proposal. And then, and this algorithm for how you accept or reject, that is chosen in such a way that the final output obeys the correct distribution function. See? So, and how do you propose the next configuration? Well, you could just use n independent units. So you could have one p bit, which has probability f of being 1 and 1 minus f of being 0, and then use n of them to propose something, and then evaluate it. And the point is, if you use this algorithm properly, then the output will come out with the right distribution. So just to give you an example, supposing you want to generate a distribution looking like this. I've taken, I think here, 4 p-bits. So there are 16 configurations in all. And what we want is these 2 configurations to stand out, 2 of them. And we want the other ones to be suppressed. So what you could do is start with a proposal which is equally distributed. So that's the yellow lines you see here. But then you use this algorithm, and what comes out at the output will have the correct distribution. It will, when you start out at t equals 1, it won't have the correct distribution, but as you go along, after some time, it will have the right distribution. And the way we construct this distribution is we do this in parallel for many runs. Here I use 10,000 runs to construct the histogram. Sometimes people collect the histogram from the time samples of a single run, but that brings in questions of whether the time samples are correlated or not. So what I prefer to do is usually have many parallel chains and construct the histogram from the parallel chains. And so if you look at the error in terms of what you're trying to get and the distribution you have, in the beginning you have a lot of error, but then after a few time steps, it goes down. And this time that it takes, that's what people refer to as mixing time or burn-in time. And that is actually very problem dependent, and no simple results for exactly how long that is. But the point is that after some time, you should have a stationary distribution, one that matches what you really want. So now you'll notice the beta here, which again motivated by statistical mechanics, where beta would be the temperature, like inverse KT. In this context, if you adjust beta, what happens is the distribution gets sharper, because it is as if you're taking whatever you had for beta equals 1 and squaring the probabilities. And so the bigger ones get bigger and the smaller ones get suppressed. But once again, with a correct beta, with a given beta, you can, as you run this sampling algorithm, you eventually get the right distribution. With larger beta, it often takes longer to get the right distribution, whereas with smaller beta, you often get the right distribution faster. And so one of the things people do in this field is this annealing. That is, you start with low beta, which is like a high temperature, and then go to high beta, which is low temperature. So you gradually start with a case when the distribution is relatively uniform, and then gradually freeze it into the right one. Anyway, so this is what I wanted to say about the sampling procedure and this Boltzmann law. And these are all, as I said, very well developed fields. There's lots of work on these ideas, and much of it is motivated by statistical mechanics, you see, where the objective was to understand natural phenomena. Whereas nowadays, there's a lot of interest in using it to solve real-world problems. And that's what I want to talk about next, which is this idea of a Boltzmann machine, where you can map interesting classical problems onto this framework that I just discussed, the one that, as I said, had been developed largely for understanding natural phenomena in the world of statistical mechanics. Now, the first example of a real-world problem that can be mapped onto this framework is just constructing logic gates. So what I mean is, so think of a, say, AND gate, which is one of the common gates that you hear about, which is like a 1-bit multiplier, essentially. So the C is the output, which is the product of A and B. And if you're familiar with electronic circuits, you know how these digital circuits are usually constructed to implement an AND gate. But what I want to describe is how you could use this Boltzmann law, this method this whole sampling method that I mentioned, to build an AND gate. And it is very different from the way you do digital circuits, see? And so the way you do it is, you see, you've got these 3 p bits, A, B, and C, and you would define your energy function so that it is particularly low for the truth table. Meaning, you see, we've got 3 p bits, so there's 8 possibilities. But of them, 4 belong to the truth table, and the other 4 are not allowed. And so what you do is you define your energy function so that the energy is low for the truth table ones, which means these 3 blue ones and the 1 yellow one here, these 4. And the other ones are all suppressed. And as I mentioned, given an energy function, if you run this Metropolis algorithm, if you go through it, you would get outputs which would follow your specified distribution function, which is high, which emphasizes all the configurations that belong to the truth table. Now, you could run it, you could say, well, how do I use it as a gate? Because as an AND gate, what should happen is, given A and B, C should follow the truth table. What you can do is, you can take the bits A and B and fix them. Let's say you fix them both to be 1. How do you fix them? Well, put a sufficient bias on each of them so that the probability of 1 is very high. So for each one. So each one of them kind of frees them into 1, 1. Well, in that case, what will happen is it will disallow all these other 3, these 3, and you won't see them. And instead, you will only see that one. See? And so you could use this as an AND gate. Now, what is interesting, though, is that usually digital gates work in one direction. You give input, you get the output. But if you construct it using this principle that I just described to you, you'd have what you might call invertible logic, where it also works the other way, in the sense that if you gave it the output, it would come back and give you the input. So let's say I decide that, well, I want to know what inputs are compatible with an output of 0. Okay, so what I can do is I'll go and fix the C, that's a C bit, and fix it to 0. Well, in that case, what will happen is that the overall system then will give me all these 3 outputs, all these 3 states, 0, 0, 0, 1, and 1, 0, and it will keep going back and forth between them. So the point is you can get all the possible inputs that are consistent with a fixed output. So this is one example of how you can map a very different type of problem onto this framework. See? Now, another one which is more, which is very interesting, but I won't go into details here, is this image classification. That where, let's say you want to recognize handwritten digits, 0, 1, 2, 3, etc. Now, each digit usually, let's say you have 28 pixels in either direction, then you have, say, 784 bits. So you'd have zeros and ones. If it's a black and white with no grayscale, then you'd have 784 bits, and the output should be 0. So in a way, you see, this is also a truth table, just that it's a very elaborate one. See, you have 784 bits, and there's a 0, and that's one line of your truth table, etc. And what you could do is, you can then, in this case, it is relatively difficult to write out the full energy function. I mean, it's a huge table, but what you often try to do is write it in this form, where there's a linear term and a 2-body term. And then what you do is you try to learn this H and J, so that you show it all kinds of images and with the proper output, and then use it to adjust the H and J so that you get so that it represents the correct truth table. And the way it would work is something like this, that let's say, you know that based on your images, the average value of S is supposed to be something, whereas the weights you have is not quite giving you what you want, but giving you something else. Then what you should do is you should go in and change this H value in this way, where this epsilon is a parameter you can adjust, this learning parameter. And how do you justify this? Well, this is what's called this contrastive divergence method of training. Some of you probably know a lot about it, but you could kind of see why this works. The idea is anytime I increase H, what it will do is it will tend to emphasize values of S which are lower because I've increased this. And so it will tend to reduce the average value of S. So you can kind of see that if what you're getting is kind of smaller than what you want it to be, you should change delta H according to, with this minus sign. So if what you're getting is less, so this is positive, then you should reduce H, because what you're getting is less, you want to make it more. So with a similar argument, you can see what you should do about the two-body terms also. But in this case, you should have to look at the correlations of SI and SJ, etc. So in this case, you see, you can show many images and thereby train this energy function with H's and J's, with these H and J parameters, so that it represents, so that it can then be used for doing inference problems. So this is just a toy example. I said that supposing you want to build a full adder. Now, full adder has two inputs, A, B, and there's a carry input from the last one. And then there's the sum. And it gives you this sum, and it tells you how much to carry. So that's the truth table of a full adder. And if you look at these and convert these to a decimal number, you'll see 0, 6, 10. These are the elements of the truth table. So you have 5 elements, so there are 32 possibilities, and the truth table are these red ones. So in the beginning, let's say all our H's and J's are 0. In that case, you see they are all equally likely to start with. But if you use this learning principle that I mentioned before, what you can do is gradually let it run, and the correct values of the truth table will gradually rise up as the H and J get adjusted. And you can go on and train the system to give you the full adder. Now, another example of a problem that you could map onto this same framework is this traveling salesman problem. That's a very well-known problem where you have a whole bunch of cities and you're trying to find the shortest, trying to find the optimal route so that the path length that you have to traverse is the smallest. So how would you represent a route with p bits? Well, the idea is any route would have a sequence of numbers like this. It's like city number 31. Then you go on to something, then city number 62, which goes to city number 11, etc. And so there will be n such numbers, and each number you could write with bits in terms of log n of bits. And so the number of p bits you need to represent a particular route would be n log n. And then you can propose different routes and use this same principle again to generate the samples. And if you have defined your energy function as the length of a particular route, so anytime you write down one, there's a corresponding length. And if you define your energy function that way, then what will happen is the highest probability outputs will be the ones with the shortest lengths. So you can start with a very bad guess. This is obviously bad. It's got a very long path length to start with. But then as you go through this procedure, eventually you can get a much cleaner path. Now, one thing in this context is that if you just make random guesses every time, then it will take a long time before you get to the stationary distribution, where you actually get nice routes with low path lengths. It is much better if you have good heuristic ways of proposing. And again, this is the field where a lot of work has been done with heuristic algorithms, which could be incorporated into our procedures. So for example, one of the methods, well-known methods, is this two-opt process, which is that supposing you currently have a path like this, then when you propose the next one, what you should do is not just propose something randomly, but take a pair of edges and flip them. So that's this two-opt process. And if you keep generating your proposals intelligently using this two-opt, for example, then what will happen is you'll clean up a bad guess like this and start getting good answers relatively quickly. Again, I'm not going into details. All I wanted to do is give you a flavor of how practical problems of interest can be mapped onto this framework. Now, what I'd like to talk about next is a little bit about mapping of quantum problems, because what I was just talking about is this mapping of everyday classical problems. Now, for this purpose, it's useful to think of I want to introduce this transition matrix, which I had alluded to earlier, because that helps see the connection to the quantum problem. So I mentioned earlier that when you start from some guess and you let this thing run, after some time, it goes to the stationary distribution. Now, one way to think about it is that every time you go through this, what happens is the probability distribution gets multiplied by this transition matrix. So this W is what's called a stochastic matrix, whose elements are all positive. And every time you go through this process, the probability distribution is getting multiplied by W. And now this W is a very big matrix, which is why as a practical tool, it's often difficult to use, this 2 to the power n by 2 to the power n matrix. But conceptually, it's very nice because it helps you kind of see what this burn-in time is and why it takes time to get to the stationary state. Because the idea is that the stochastic matrices have this property that it has all positive eigenvalues, and the largest eigenvalue is 1. So the stationary distribution is basically the eigenvector that corresponds to this eigenvalue of 1. Because once you have the stationary distribution, multiplying by W just gives you the same distribution back again. And that's why at some point, it settles down to a fixed distribution, you see. So this stationary distribution is this eigenvector, which corresponds to the eigenvalue of 1. But then there are other eigenvalues which are less than 1. And it takes some time when you start from a bad distribution, it takes some time for those other eigenvectors to die out. And how long does it take? Well, it depends on how close the eigenvalue is to 1. Because if the eigenvalue was, say, 0.5, then every step it would go down by a factor of 0.5 and it would quickly disappear. But if the eigenvalue was, say, 0.9999, then every time it would go down by 0.9999 and it would take a while to go down. So burn-in depends really on those eigenvalues. So conceptually, this is very powerful. But as I said, as a practical matter, the utility is limited because W is such a huge matrix, hard to write it down, find its eigenvalues, etc. Now, but conceptually, the way you think is when you start from some initial state, what is happening is the final state is obtained by multiplying with a sequence of W matrices. And usually all matrices are the same, but in principle, as you go along, you could even change it with time so that at each instant of time, you'd have a different W. So I kind of wrote it in a more general way. But but for what we had discussed earlier, every W would be the same. And you can use these rules of matrix multiplication to kind of write it out in terms of, write out this matrix multiplication as if you're going through, different states. So you could use this, when you write out this matrix multiplication, each term here, which you have to add them all up, each term here could be viewed as a particular path leading from the initial to the final state. And the actual probability is like a sum over paths. See, this is kind of like this Feynman path integral, but of course here it's a Feynman's sum. But basically it is a nice pictorial way of thinking of these matrix multiplications. See? Now, the way sampling works is that, well, you have got an enormous number of paths to sum over. What sampling does is it selects a few paths and selects the ones with the highest probability, adds them up, and that's how it tries to get a good estimate of the correct answer. See, in a way. Kind of like doing an exit poll to try to predict an election, right? And you're selecting a few and trying to draw conclusions from that. So now, and this concept applies even to feed-forward neural networks. I introduced this Boltzmann machine where there were all these p-bits were all coupled together, but you could also think of feed-forward neural networks in much the same way, where you have these W matrices and you're basically summing over paths. But more interestingly, the reason I brought it up is it shows nicely the connection to quantum gates, to quantum circuits. Because in the quantum case, what happens if you have this gated quantum computing, you are multiplying with these unitary matrices U. And you'll notice again, mathematically, they are very similar. You see, here you have these positive probabilities getting multiplied by stochastic matrices. Here you have these probability amplitudes, which are complex quantities, getting multiplied by unitary matrices. But just as you could interpret this as a sum over paths, many paths with probabilities that are getting added, in the quantum case, you could think of it as, again, same paths, but each has a complex amplitude, which is getting added up. And you could use the same sampling methods for quantum problems as well. It is just that instead of adding all positive numbers, you'd now be adding complex numbers. And when you add complex numbers, it is a little more difficult to converge to a proper solution because complex numbers can cancel out, whereas positive numbers would always add. But you could view it again as a Boltzmann machine. It's just that now the elements here are complex. And so if you try to write it as in terms of an energy function, that energy function would be complex. So it is as if you have a Boltzmann machine with complex energies. Now, that's gated quantum computing. And then there is another branch, which is adiabatic quantum computing, where you want to find this density matrix, e to the power minus beta h being a matrix. And there again, there's this Suzuki-Trotter transformation that one can use to evaluate this quantity by breaking it up into R set of replicas. That is e to the power minus beta h over R multiplied R times. And there again, you'd have these paths that you are adding up. So it maps much to the same mathematics. Now, and here there's an interesting point is that in gated quantum computing, usually these quantities are always complex, but in adiabatic quantum computing, often the elements may be real and have the same sign, in which case you refer to this as stochastic problems. So, I mean, a combination of this stochastic and quantum. And if it's stochastic, then you see all the paths are positive. And so there is no cancellation issue. And then a probabilistic evaluation should work quite effectively. See? Okay. Now, that brings me to the final point that I wanted to discuss with an example. So I think, we have gone through how this general concept of Boltzmann law and Boltzmann machines, how you map classical problems, how you map quantum problems. And now now what I want to describe to you is how you could build a Boltzmann machine. And question is, would that lead to any advantage over just a direct implementation in software? You see, whatever I've described to you until now, these different algorithms, these different ways of mapping, all that you can implement on your laptop, using software. You write a code. You could write a MATLAB or Python or C++ codes, and you can implement it. Now, the question is, and if you do that, they would be comparable to many state-of-the-art algorithms. Depends on the problem at hand, where they stand with respect to state-of-the-art algorithms. But what I'd like to point out, and that's this final part of the talk, is that if you implement it with specially architected hardware, then they could lead to a lot of acceleration of the computation. So it could lead to very competitive results. And that's what I'd call a physics-inspired probabilistic computer. See? So the idea is that, you see, when you're proposing this next configuration, I'd mentioned that you'd use these NP bits. And usually, to construct one of these p bits using CMOS technology, and we have done just that, it takes thousands of transistors. Whereas if you use a fluctuating resistor, that is, there is this magnetic tunnel junction. I'd earlier mentioned that magnets, when they become small, they tend to fluctuate. And you could use that to build a resistor whose resistance would fluctuate with time. And so it would give you a natural p bit. And in fact, the way we got interested in this whole field was, you see, we were working on these magnetic tunnel junctions, and we realized that it could be used to build a p bit. And you could build a little compact unit like this with 3 transistors and a MTJ, which would replace thousands of transistors if you are trying to implement it with standard CMOS. And so we got interested in looking at what you could do with this unit. See, that's how we kind of backed into it. But of course, everything I'm saying, all of this is more general. There could be other representations, other physical ways of building these p bits. But now, let me we have looked at many problems over the years. And so let me just tell you a little bit about, I'll just choose one problem to illustrate the point. Okay. So this is an interesting problem that was published like in 2021. And it's a quantum problem, actually. So there's a lattice of qubits with this particular lattice. And this is a problem that actually is a stochastic problem. And so ordinarily, you might have thought that there would be the probabilistic evaluations should be quite effective because there's no cancellations, none of the sign problem involved. But what this paper showed was that when you take this problem and implement it with a quantum annealer, it actually gets you results that are like 6 orders of magnitude faster than what you get on a CPU. And so what we set out to understand is, where does that 6 orders of magnitude come from? How much is due to quantum, or are there other factors that are getting into this? And so what we did was we did the same problem using this Suzuki-Trotter transformation with 10 or 20 replicas, which in this case seems adequate to get accurate results. So replicas means that if you have this particular lattice, what you do is create a lattice where you have similar looking layers, each layer looking just like the qubit lattice. And then in the vertical direction, these various replicas are coupled by a certain strength, which is determined by the strength by the degree of this quantum, this is the transverse-Ising model. So it has this x-directed coupling, and that's what determines these coupling between replicas. But at the end, you see what we are dealing with is a sort of a Ising model with a bias term and an interaction term, but it's a three-dimensional lattice, really. That's what you're trying to do. Okay. Now, what was shown in that paper was that using this sophisticated cluster algorithm implemented on CPU, the time to solution versus the size of the lattice, number of qubits in the lattice, and you're comparing what you get on CPU compared to what the quantum annealer gets. And you can see there's this 6 orders of magnitude difference. And this is what we try to understand. So, and as I said, we are kind of puzzled by this just because, there is this, that the general idea is that if you do not have a sign problem, then the classical methods should work fairly well. Because, this is a quote from Feynman in the paper, this is the seminal paper that inspired a lot of the work on quantum computing, where he said that the only difference between the probabilistic world and the quantum world is this sign problem. It's as if the probabilities are negative or more generally complex. And since this particular problem was stochastic, we didn't have this difference. So it should be possible, you'd think, to bridge this 6 orders using classical methods. And so one of the things we did first is used an FPGA, this field programmable gate array. And those of you who are familiar, you probably know this, is that allows you to configure your hardware appropriately for the problem. So in this problem, what happens is that, you see, ordinarily what the CPU does is when it evaluates proposals, it goes at it one by one. So it first goes and says, okay, let's update this particular lattice site. Next, we update that one, and that one, and that one, and so on. And this is important because you don't want to update simultaneously 2 sites which are connected to each other, because then it is well known that you won't quite go to the right distribution. But the interesting thing about this lattice is that you can kind of color it like blue and red, as we have shown, so that the blues are all unconnected and the reds are all unconnected. So it is as if there are 2 separate lattices. And that's what's generally called this graph coloring, so that you can update all blues at the same time, and you can update all reds at the same time. And that wouldn't incur any errors. So that's what we did here. You see, and the FPGA allows you then to do it all in parallel, all reds in parallel, all blues in parallel. You configure the hardware, so it does that. And you can see it gets you about 3 orders of magnitude improvement right there. And another important thing is the scaling thing, that the usual CPU algorithm goes as n squared, whereas when you do this, it actually increases more like n. And the reason is, of course, you're updating n over 2 lattice sites simultaneously. So that's why instead of an n square increase, you get an increase by n. Now, actually, it takes some amount of work to design this FPGA properly. And that's because, you see, it's not enough just to propose a lot in parallel. You also have to evaluate them efficiently right there without having to access memory and things like that. And what we did was set it up so that every clock cycle you could propose and evaluate as well. And so that at the end of the day, we were getting n over c samples, c being the number of colors, which in this case is 2. Every clock cycle, every 8 nanoseconds, we are getting n over c samples. So unless you design it properly so that it's properly pipelined and all that, you won't quite get this 3 orders of magnitude improvement. So what I want to stress is this 3 orders of magnitude improvement requires very careful design of the hardware, the proper architecture. But once you can do that, you get this significant improvement here. Now the question is, you see, we still have a big difference with the results for the quantum annealer that were quoted in this paper. And we're then trying to understand where that could be coming from. And this is where what we project is that if you went to instead of this digital circuit, this clock digital circuit, if you had actually implemented this with an unclocked circuit, you could get another factor of 100 or 1,000. So exactly how much, this is a projected thing, and I'll explain what is the basis of our projection. So, but there could be a significant improvement going from this digital clocked version to an unclocked version. So what do we mean by the unclocked version? Well, where your P bits are all based on these MTJ type of units that I had mentioned before, this compact units that I had mentioned, and the delta E evaluation, you see, this involves this Jij, Sj, and these, what you could do is implement these with resistors, where the J becomes a resistor. And that's what is done here. All these different units are connected with resistors in such a way as to implement this energy function appropriately. See? And when we do that, what we find is that, you see, we had this digital implementation of the same thing. And with the digital implementation, again, I mean, the two are almost isomorphic in the sense that here you have this compact unit for the P bit. Here you have a digital version, which requires thousands of transistors. Of course, it's much bigger, but otherwise the architecture is very comparable. And the thing is that when you run the digital one, let's say you get whatever you're computing, this solution, it gradually over time gets to the right value. Whereas when you do this circuit, it also goes to the right value, and it is, and what we have done is a SPICE simulation, and that's this blue curve. And you can see that the blue and the red are very comparable curves. The difference though is, you see the red curve we have is actually much, much slower. We had to scale it in order to make it fit. How did we scale it? Well, you see, usually what would have happened is 8 nanosecond is our clock cycle of the FPGA, the digital. But in order to fit what we get from the SPICE simulation, we had to scale it from 8 nanosecond to 20 picoseconds. That's a factor of 400. So the point is that this clockless circuit, this analog circuit, it functions almost like an FPGA that's not 125 megahertz, but more like a 50 gigahertz FPGA. So it is functioning much, much faster. And so the point I'm trying to make here is that just by going into this clockless version, it could be operating much, much faster, as if it has got a very fast clock, you see, compared to the digital. But of course, what it implies, you can only do that if you have this compact implementation where these the delta E evaluations can be done simply with resistive networks and so on. So if you can do that, then you could have this improvement. And that is the basis for this projection that we make here. That, okay, here's what we got with the 125 megahertz FPGA, but if you had an unclocked circuit, you could have another factor of a few hundred acceleration. And this one could argue exactly how much this could be, whether it could be a little bit lower as well. And one thing not completely sure is we still have a difference with the quantum, but you notice that the original 6 orders of magnitude, much of it you can improve just with various classical things. The FPGA, which does the parallel which implements all the updates in parallel, and then this unclocked version where you are effectively working as if it's got a very fast clock. Now, one thing you might wonder is, well, this one doesn't have any clock, but don't we have to worry about coloring, namely making sure the reds and the blues don't update simultaneously? And what we have found is that it actually doesn't matter as long as the p bits flip on a time scale that is much slower than the RC times. Because this is one thing I'd always wondered, that always made me wonder, is the digital circuits require this clock to update things regularly. And yet natural systems, of course, don't work with clocks. And what we have shown is that, yeah, you don't really need the clocks if those delta E evaluations occur on a fast enough time scale compared to the rest of it. If they're slow, then of course that will completely mess it up. But if they're fast, then you don't really need the clocks. And now, whether there is, after you have done all the things you can do classically, whether there'd still be some difference with the quantum, that we are not completely sure. Because I know that there are papers which say that the quantum Monte Carlo could give you a quadratic speed up over the classical. And this is the part that we don't yet, we're not completely sure whether there is a basic difference at the end with quantum in a problem like this where it's stochastic. Because of course, if there's sign problem, then we know the quantum can have an advantage because it evaluates these Feynman's, this sums that have a sign problem, it can do that very much more efficiently. So yes, so that's basically the message I wanted to convey, that this Boltzmann law, Boltzmann machine, these are very general concepts, and there's lots of problems that can be mapped onto them, including many quantum problems. And these you could, of course, implement in software today on your laptop. But if you want to get major acceleration, then one needs to kind of take these two steps. One is, firstly, try to implement things in parallel, and their FPGA allows you to reconfigure the hardware for that. And then I think one could gain a lot more again by making use of this unclocked operation. Thank you.
Thank you very much, Dr. Datta, for the presentation. Virtual applause here, I guess, looking across the attendees. We have time for a few questions. Feel free to raise your hand and I'll call on you